Welcome to the deep dive. Our mission is to take the complex, the obscure, and the dense like a stack of scientific papers on quantum physics and distill it down into the most essential, fascinating knowledge you can possibly absorb.
We're giving you that shortcut to being truly well-informed.
And today we are embarking on a journey to the coldest possible physical limit in existence.
We are plunging into the physics of absolute cold, a deep dive into absolute zero.
So let's define our target right away. We are talking about 0 Kelvin. That's a capital K.
Right. And if you live in the Celsius world, that's precisely minus 273.15 degrees.
And if you're still using Fahrenheit, just remember this chilling number. Minus 459.67 degrees.
But this is so much more than just a temperature reading. It's a fundamental theoretical barrier.
It really is. And our deep dive today is a journey through history to see how that limit was even discovered in the first place.
And then through thermodynamics and quantum mechanics to understand why we can never actually reach it.
And from there, we'll get into the really exotic stuff, these states of matter like Bose-Einstein condensates found in the deepest cold of laboratories in the most remote corners of space.
And that really gets to the core paradox we'll be wrestling with.
Yeah.
Absolute zero is this unachievable fundamental limit.
The third law of thermodynamics makes sure of that.
Exactly. But, and this is the amazing part, scientists are getting so incredibly close. They're achieving record temperatures measured in trillionths of a Kelvin.
We're talking about the picokelvin range.
The picokelvin range.
Mm-hmm.
And doing so reveals physical phenomena that completely redefine our understanding of matter. That chase, the physics revealed right at the wall, is where it gets truly amazing.
Okay, so to get to that wall, we have to start at the beginning. How did we even know there was a wall to begin with?
Well, to understand the modern quest, you have to realize that the existence of a minimal temperature was inferred centuries ago.
Long before we had accurate thermometers.
Long before. They did it just by using observations of simple gases. It wasn't a sudden discovery. It was more of an extrapolation.
And that extrapolation began with the ideal gas law. It's one of those beautiful pieces of classical physics that just gives you a universal truth.
It does. I mean, imagine an ideal gas. It's a hypothetical thing, right? Particles are just non-interacting points, purely theoretical, but it's super useful.
So what was the observation?
It was straightforward. If you take a fixed amount of this gas and you keep its volume constant, the pressure decreases perfectly linearly as you cool it down.
Okay.
And if you do the same experiment but, keep the pressure constant instead, the volume decreases linearly with temperature. A perfect straight line.
So if you just plot that line, what happens when you keep going? When you continue the cooling process, in theory?
And that is the crucial historical insight. When 18th and 19th century scientists plotted these experimental observations using the Celsius scale, which remember was totally arbitrary, based on water's freezing point.
Right, it's just a human invention.
Exactly. They saw that if they just continued that line downwards, cooling the gas linearly, both the volume and the pressure would theoretically disappear at the exact same point.
Which was roughly minus 273.15 degrees Celsius.
Precisely.
But wait, volume and pressure disappearing? That implies zero motion, zero energy in the particles. So if you cool past that point, what happens?
You enter the realm of the physically impossible. You can't have negative pressure or negative volume. It just doesn't make sense.
So that point where those properties vanish mathematically, that must be a fundamental physical lower bound on temperature.
It has to be. For a classical system, it represents the absolute cessation of all molecular motion.
And that, I guess, is the definition of the Kelvin scale. It takes that physical reality and anchors the whole system there, rather than at the arbitrary freezing point of water.
That's exactly what Lord Kelvin did. He saw this and said, if this point is the absolute minimum, then this is where zero must be. The Kelvin scale sets its 0.0 K precisely at this lower bound.
Which makes it an absolute scale.
Right, where temperatures are finally fundamentally proportional to the energy content of the system.
It's just fascinating how this theoretical limit started as a thought experiment, really, based on the simple measurement of air pressure. But let's go back even further to the philosophical quest for the degree of cold.
Oh yeah, this concept isn't new at all. It has roots way back in the Renaissance. In 1665, the natural philosopher Robert Boyle published new experiments and observations touching cold.
And he was dealing with this older idea of the primum frigidum, the supremely cold body.
Yes, the naturalists were already debating whether cold was just a lack of heat or if there was some substance or state that was inherently, universally cold.
They were looking for a universal zero.
A universal zero. But the first scientist to seriously put a number on this zero point using a measurement device was Guillaume Emmons in 1703. He was instrumental.
How did Emmons approach the problem? I mean, what was his setup?
He used an air thermometer. It measured temperature by tracking the height of a mercury column that was supported by the pressure, the spring, as he called it, of the confined air inside.
So he was performing that same linear extrapolation we just talked about, just more intuitively.
Exactly. Amundsen argued that the zero point of his scale had to be the temperature at which the air's spring, its pressure, was reduced to nothing.
And what did he estimate?
He estimated it to be about minus 240 degrees Celsius. What's astonishing is how close that is to the modern value, minus 273.15, given the crude instruments he was using.
He knew he could never reach it, but he gave the first compelling numerical estimate.
He did, and that line of inquiry was quickly refined by others.
Right. I remember reading about Johann Heinrich Lambert.
Lambert, in 1779, improved the extrapolation. He suggested absolute cold was closer to minus 207 degrees Celsius.
Yeah.
But this was far from a consensus. He had figures like John Dalton, the atomic theory guy. He initially adopted minus 3,000 degrees Celsius as the natural zero in his early work. It just shows how wildly divergent the views were before a unified thermodynamic theory emerged.
So the stage was set then for someone to provide a robust, non-empirical foundation, and that someone was William Thomson, Lord Kelvin.
Thomson, starting around 1848, formalized the whole concept. He built on the work of James Prescott Joule and Sadi Carnot's theories on heat engines, and this was the genius of his approach. He devised a scale that was entirely theoretical.
So it was derived from the efficiency of a hypothetical perfect heat engine.
Yes, meaning his scale was independent of the properties of any physical substance. No reliance on air pressure or water freezing points.
It was based purely on thermodynamic principles.
That is the defining feature. The absolute zero point on Kelvin's scale was the temperature at which a perfect Carnot engine would exhaust zero heat, meaning 100% efficiency would be possible.
And his theoretical zero, calculated from these fundamental principles, landed almost precisely at the same point as the one from the air thermometer.
At minus 273 degrees Celsius. That dual validation, the theoretical and the empirical converging on the same number, that must have been immensely powerful for the scientific community.
It solidified the universal nature of the limit. It proved absolute zero wasn't just a property of air or any one gas. It was a fundamental property of the universe's energy structure.
And that gave scientists the certainty they needed to dedicate labs and decades to the seemingly impossible task of trying to get there.
Okay, so we've established where absolute zero is. But the great frustration for scientists remains. We can get arbitrarily close, but we can never actually touch it. It's a wall.
It is a hard wall.
And the first, most formidable blockade is the third law of thermodynamics.
That's our thermodynamic sentinel. The third law governs the behavior of entropy, which is the measure of disorder or randomness in a system, as the temperature drops towards 0K.
It states that the entropy of a system approaches a constant minimum value as the temperature approaches absolute zero.
Correct. So in a system that's perfectly ordered, like a perfect crystal, that minimum entropy value would theoretically be zero. No randomness at all.
But the third law also imposes what's called the unattainability principle.
It does. And we often use the Nernst heat theorem to explain it, which is effectively another formulation of the third law.
So what does the Nernst theorem tell us?
It states that the change in entropy for any constant temperature process, any cooling step, tends towards zero as the temperature itself approaches zero.
So if you're trying to cool something from, say, 1 Kelvin down to 0.1 Kelvin, that step reduces the system's entropy.
Right. But the closer you get to 0K, the smaller that reduction in entropy becomes. So the process of removing heat becomes exponentially less efficient.
I get the diminishing returns, but why does it become infinitely inefficient right at the very end?
Because every cooling method we have relies on a reduction of entropy. To reach 0K, you would need a cooling process that achieved zero entropy change, which is impossible without, infinite resources or infinite time.
It's like trying to wash a dish perfectly clean.
That's a great analogy. You can remove 90% of the dirt in the first pass, then 90% of what's left in the second, and so on. You can get arbitrarily close to clean, but mathematically you'll always have some tiny residual amount left.
So the third law implies that no physical process, whether it's cryocoolers or laser cooling, can cool a system to absolute zero in a finite number of steps or within a finite time. It's the ultimate law of diminishing returns.
It is the practical barrier that defines the entire field of cryogenics. But once we get past that thermodynamic wall, we immediately hit a second wall,
The quantum mechanical
the
one.
quantum wall. And this one explains why, even theoretically, matter can never be truly still. This is where classical physics just completely failed near this limit.
And this brings us to the behavior of electrons in metals, which is described by the Fermi gas model.
Yes, late 19th century classical physicists were completely baffled by metals. They expected that as metals cooled, their specific heat, the energy needed to raise their temperature, should change dramatically.
Because it should reflect the reduction in molecular motion.
Exactly. But it didn't. They didn't understand why the electrons didn't seem to stop moving.
And the quantum world provides the answer. We have to abandon the classical equipartition theorem.
We do. The electrons in a metal are fermions, and they have to obey the Pauli exclusion principle.
No two electrons can occupy the exact same quantum state at the same time.
Right. Which means that as you cool the system down, the electrons can't all just collapse into the lowest possible energy level. They have to fill up higher and higher energy states, like water filling a bucket from the bottom up.
So this forced occupation means that even if the metal were at absolute zero, those electrons at the top of the pile would still have enormous kinetic energy.
Exactly. They are in motion not because of thermal energy, but because of a quantum requirement. We quantify this residual energy using something called the Fermi energy.
And if we translate that energy back into a temperature, the Fermi temperature, what kind of number are we talking about for a typical metal?
We're talking about a value on the order of 80,000 Kelvin.
80,000 Kelvin. That's a fiery core of motion inside what we're calling a cold metal.
It explains the classical failure beautifully. I mean, if the electron's mandatory energy floor corresponds to 80,000 K, then cooling the metal from room temperature 300 K down to near absolute zero is a tiny relative change.
The electrons are already behaving as if they're near absolute zero because 300 K is so far below their Fermi temperature.
That's why the classical expectations about specific heat just didn't hold up. The change is tiny until you get extremely close to 0 K, and then it finally drops.
That motion is just inherent. And even if we step away from a Fermi gas and look at single atoms, we still find this quantum mechanical shiver that is zero-point energy.
Zero-point energy, or ZPE, is the second fundamental quantum roadblock, and it's mandated by the Heisenberg uncertainty principle.
Which prevents us from defining a particle's position and its momentum perfectly at the same time.
Right. If we reach 0 K, that would imply zero momentum, which is a perfectly defined value.
Which would, in turn, mandate infinite uncertainty in position, meaning the particle would be spread out across the entire universe.
Which is clearly impossible. So even at 0 K, the system has to retain some residual energy just to maintain that uncertainty relationship. That minimum residual energy is the 0-point energy.
So we can remove the thermal energy, but the ZPG always remains. It's like a quantum floor vibration that you can never silence.
That's a good way to put it. The simplest model, the quantum harmonic oscillator, which models atomic vibrations, must possess a non-zero minimum energy state, even at its ground state.
And the ultimate physical proof of this, smoking gun of ZPE in action, has to be liquid helium.
Absolutely. Liquid helium-4 is the textbook demonstration. Helium atoms are very, very light, and they interact with only weak van der Waals forces.
So you combine their low mass with the disruptive force of this large zero-point motion, that inherent quantum shiver, and it prevents them from settling into a rigid, solid structure.
It does. It means that even when you cool helium down to temperatures right above absolute zero, it just remains a liquid under ambient pressure.
It stays a liquid.
It requires significant external pressure, around 25 atmospheres, to force those atoms close enough together for the weak interatomic forces to finally overcome that disruptive ZPE motion and lock them into a solid lattice.
So ZPE keeps liquid helium perpetually fluid under normal conditions, proving that even the quest for absolute physical stillness is fundamentally denied by the laws of the universe.
The theoretical understanding of absolute zero in the mid-19th century immediately sparked what was probably the greatest experimental challenge of the age.
The race to liquefy every single gas.
That's right. This was the first stage of the cooling race, the age of liquefaction. It started with Michael Faraday back in 1845, who set an initial record of minus 130 degrees Celsius.
But Faraday, like most scientists then, believed that certain gases, oxygen, nitrogen, and especially the light ones like hydrogen and helium, were permanent gases.
They thought these gases were just fundamentally impossible to liquefy.
A belief that was soon shattered by theory, much like those classical physics models were shattered by the quantum world.
In 1873, Johannes Diederik van der Waals provided the theoretical framework. He showed that all gases could be liquefied, but they each possessed a critical temperature. Above that temperature, no amount of pressure would turn it into a liquid.
And that established that the permanent gases just had extremely low critical temperatures. You needed both high pressure and extreme cooling.
Once that theoretical barrier was broken, the experimental race began in earnest. The record started falling rapidly in the 1870s.
You had Louis-Paul Cailletet in France and Raoul Pictet in Switzerland getting the first droplets of liquid air around -195 C in 1877.
Then in 1883, Polish professors Wróblewski and Olszewski pushed even lower, getting liquid oxygen at -218 C.
But the final gases, hydrogen and helium, led to one of the most intense scientific rivalries of the era, didn't they? The clash between James Dewar and Heike Kamerlingh-Onnes.
Oh, it was a true scientific feud. It was fueled by immense ambition, and particularly on Dewar's side, a lot of secrecy. James Dewar, the great Scottish chemist, was focused on hydrogen.
He's the guy who invented the vacuum flask, the Vermis.
He did, which was essential for cryogenic storage, but he fiercely guarded his experimental methods. He basically invented the fundamental piece of equipment necessary to store the thing he was trying to create.
And after 2 decades of persistent work, he was the first to liquefy hydrogen in 1898.
He was. He achieved a temperature of -252 degrees Celsius, or 21.1 Kelvin. He was within a gasp of the final prize.
But the last element, the hardest to cool, was helium. And that ultimately fell to his great Dutch rival.
Heike Kamerlingh-Onnes. He worked in Leiden and established an entire cryogenics facility focusing on systematic precision. And in 1908, using sophisticated multi-stage pre-cooling and something called the Hampson-Lindh cycle.
Which uses the cooling effect when a compressed gas expands rapidly.
Exactly. He liquefied helium.
That put the temperature record at 4.15 Kelvin, a stunning achievement for the time.
And he immediately pushed it further by evaporative cooling, just reducing the pressure above the liquid helium, and took the temperature down to 1.5 K.
This was the coldest temperature ever recorded at the time and earned him the 1913 Nobel Prize.
More importantly, working at these unprecedented temperatures, he immediately discovered superconductivity. He demonstrated that this boundary wasn't just a technical challenge, but a key to unlocking entirely new physics.
So let's fast forward a century. We went from 4 Kelvin using liquid helium to modern systems using incredibly complex techniques. Now we're fighting in the picokelvin range.
Right. Once you're below 4 Kelvin, liquefaction is no longer efficient. You move into techniques like adiabatic demagnetization and eventually to laser cooling and evaporative cooling of atomic gases.
That shift from chemical processes to pure quantum mechanics is profound. But we should clarify one early dramatic record.
Yes, the 2000 nuclear spin temperature record set in Helsinki, Finland. They achieved temperatures below 100 picokelvin.
An astonishing feat.
It was. But it's critical to understand the nuance. This was the temperature associated with the nuclear spin property of the material. The overall thermodynamic temperature of the bulk material was still higher.
So they managed to isolate and cool just one specific quantum degree of freedom.
Correct. So if we're talking about the undisputed world record for the overall effective temperature of matter, what is it and how did they do it?
Okay, what is it?
The current world record for effective thermodynamic temperature was set in 2021 by a German team. And they achieved an almost unbelievable 38 picokelvin.
38 trillionths of a Kelvin above absolute zero.
38 parts in a trillion. That sounds like an engineering nightmare to even measure.
And the way they achieved it involves a fantastic piece of lateral thinking because they had to actively eliminate the effect of gravity.
That's the key innovation. Gravity introduces noise and forces the gas cloud to settle and interact with the trap walls. So to minimize this, they took their experimental apparatus.
Which was a Bose-Einstein condensate of rubidium atoms trapped in a magnetic field.
Right, inside a vacuum chamber. And they took it to the European Space Agency's Bremen drop tower.
So they weren't just cooling it on the ground and then dropping it, they were using the drop itself as part of the cooling process.
Precisely. They dropped the entire vacuum chamber down the 120-meter drop tower, which provides about 4.7 seconds of high-quality microgravity.
And during the free fall,
They rapidly switched the magnetic field, holding the gas on and off a process called adiabatic expansion. This minimized the atom's molecular motion to nearly nothing, kind of mimicking the stillness of deep space.
So the atoms weren't actually in space, but they were in free fall, effectively weightless, allowing the cooling technique to work without that gravitational interference.
That's it. In those brief seconds, they managed to hold that record-breaking temperature of 38 picokelvin for about 2 seconds. The researchers even noted that if they had access to truly weightless conditions, like on the International Space Station, they could sustain this temperature for far longer.
Maybe up to 17 seconds.
Potentially, yeah, allowing for much more detailed study. It dramatically surpassed the previous record and marked a new era in ultra-cold precision.
And the only reason these record-breaking experiments are even possible is because of the exotic matter they create. The Bose-Einstein condensate, or BEC, this is often called the fifth state of matter.
It is a remarkable state.
Yeah.
BECs are these highly diffuse gases that exist only under ultra-cold conditions, often 40 to 70 billionths of a degree above absolute zero.
And to understand a BEC, we have to go back to the fundamental idea that matter has wave properties.
Back to Louis de Broglie's hypothesis from 1924, particles behave as waves.
Right. Every particle has a matter wavelength, which is inversely proportional to its velocity. At room temperature, particles are zooming around, so their wavelength is minuscule, far smaller than the atom itself. We just don't notice it.
Okay, so if the wavelength is tied inversely to velocity, what happens when you slow the atoms down by cooling them to nanokelvin temperatures?
The velocity drops dramatically, and so the de Broglie wavelength increases dramatically. It shifts from being subatomic to becoming macroscopic.
Meaning the quantum wave associated with the atom is now physically large, comparable in size to the distance between the atoms themselves.
And this is the breakthrough insight for BECs. When the waves start overlapping, the atoms stop acting as individuals.
Precisely. When the thermal jitter is so low that the matter wavelengths overlap, all the individual atoms, which must be bosons like rubidium-87, they all fall into the lowest available quantum state.
So they stop existing as independent particles.
And they begin behaving collectively as one giant matter wave, oscillating completely in phase. It is quantum mechanics expressed on a macroscopic scale.
And that single coherent quantum state acts almost like a pristine quantum laboratory. What kind of experiments does this enable, especially in the field of atom optics?
One major area, pioneered by Wolfgang Ketterl's Nobel-winning work at MIT, is the development of atom lasers and atom amplification. It draws direct parallels from optical lasers.
A BEC can serve as an incredibly intense, coherent source of ultra-cold atoms.
Exactly.
But an optical laser amplifies light photons by stimulated emission. How does an atom amplifier work if you can't simply create new atoms?
That's the critical difference. An atom amplifier doesn't create atoms, it converts them. So think of the BEC as a massive, still pool of resting zero-energy atoms, all in the same quantum state.
The reservoir.
The reservoir.
Hey.
If you introduce a small incoming atomic wave, the amplifier converts atoms from that resting pool into the exact same quantum state as the input wave.
How is that conversion physically managed?
They use specific laser light scattering. The light provides the necessary recoil, the energy and momentum kick to accelerate a resting atom from the BEC reservoir so that it perfectly matches the velocity and quantum state of the incoming signal wave.
So the laser is essentially acting like a quantum copier, forcing the reservoir atoms to mimic the input.
Exactly. It's known as bosonic stimulation. The process augments the input waves, meaning the output atomic pulse contains many more atoms than the input did.
And in early experiments, amplification factors were, what, 10 to 100?
Typically, yeah. And this capability to amplify quantum matter waves is hugely significant.
Because if you can amplify atom waves, you can dramatically improve the sensitivity of devices like atom interferometers, which are used for the most precise measurements of rotation, gravity, and acceleration.
It takes the quantum wave nature of matter and gives it practical utility. And beyond amplification, BECs are essential for studying fundamental quantum fluids, specifically via vortices.
Another macroscopic quantum phenomenon?
It is. We see classical vortices like whirlpools all the time. But in a quantum fluid, they become quantized.
What does that actually mean?
Well, when you spin a normal fluid, the velocity increases smoothly from the center to the edge. It rotates rigidly. A superfluid, however, cannot do that. Its internal structure has to satisfy strict quantum mechanical rules.
Specifically, the circulation must be quantized, which means the fluid develops singularities instead of a smooth flow.
Correct. The only way for the system to satisfy the quantization rule is to develop these singular regions, which are the quantized vortices. They're tiny, perfect whirlpools where the quantum mechanical phase changes by exactly 2 pi when an atom goes around the empty core.
So how do you induce and then observe these structures in the lab?
Ketterl's team stirred the gaseous condensate with a focused laser beam, causing the ultra-cold gas to rotate. And they observed this remarkable macroscopic manifestation. The vortices crystallized into highly ordered triangular
A
patterns.
lattice.
A lattice. It's known as an Abrikosov lattice, which was first predicted for flux lines and superconductors. They managed to image arrays of up to 130 vortices in a gas cloud that was incredibly tenuous, 100,000 times thinner than air.
How could they possibly see them?
Well, the vortex cores are too small to see optically, so they turned off the magnetic trap, allowed the gas to ballistically expand 20-fold, and then imaged it. The empty cores, where the atoms had been expelled, appeared as blight spots in the expanded structure.
Which allows them to study the dynamics of quantum turbulence and how energy decays in a perfect fluid system. You're essentially watching the rules of quantum mechanics written in a cloud of gas.
So we've established the lowest theoretical limit and laboratory records. Now we have to step out into the vast, cold domain of the universe itself.
And the average temperature of the cosmos provides a profound baseline. That baseline is the cosmic microwave background, or CMB.
Precisely. The CMB radiation sets the universe's temperature at approximately 2.725 Kelvin, minus 270.42 degrees Celsius. And this ancient light is the single most compelling piece of evidence we have for the Big Bang theory.
What exactly is this light a relic of?
You have to picture the early universe. For the first 379,000 years after the Big Bang, the universe was this incredibly dense, opaque fog of hot plasma.
It was a blinding soup.
It was. Electrons and protons couldn't combine because the temperature was just too high, meaning free electrons immediately scattered any passing photons. The light was trapped.
But as the universe expanded, it cooled. And once the temperature dropped to about 3,000 Kelvin, the recombination epoch occurred.
Electrons finally combined with protons to form stable neutral hydrogen atoms. And critically, neutral atoms do not scatter thermal radiation nearly as effectively.
And the universe suddenly became transparent.
In that moment, the photons decoupled from matter and began traveling freely through space. We detect these photons today, appearing to originate from a surface far away called the surface of last scattering.
So the expansion of the universe since then has taken that 3,000 K light and stretched its wavelength, redshifted it, until it's now just faint. 2.725 K microwave static coming from every direction.
That expansion is the reason the universe is so cold today. The CMB is often called the most perfect black body spectrum ever measured in nature. It's a perfect confirmation of its origin.
The CMB appears remarkably uniform across the sky, isotropic, but cosmologists get their richest insights from the tiny temperature variations within that uniformity.
Those tiny differences, the anisotropies, are everything. The CMB is uniform to about 1 part in 25,000, but the tiny temperature variations are just over 100 microkelvin.
And these faint ripples are essentially the density structure of the early universe, frozen in time when the light decoupled.
They are the seeds of everything we see today: galaxies, clusters, and voids. When we analyze these anisotropies, we look at the power spectrum, which is the distribution of ripples of different angular sizes.
And the spectrum reveals a distinct pattern of peaks and valleys, the acoustic peaks.
We call them that because before recombination, the plasma was so dense it behaved like a fluid, and density fluctuations propagated as sound waves. The peaks represent the moments when a specific wave size reached maximum compression just as the light decoupled. It's the ringing left over from the universe's initial conditions.
And that ringing pattern acts as the ultimate ruler for cosmology, doesn't it?
Absolutely. The angular scale of the first acoustic peak is arguably the most important data point in modern cosmology. It determines the overall curvature of the universe.
And measurements confirm the universe is approximately flat.
Within a very narrow margin of error, yes. Then the ratio of the odd to even peaks dictates the density of ordinary matter, the baryons. And the height of the third peak gives us crucial information about the density of dark matter.
And beyond temperature, the CMB also contains information encoded in its polarization.
Correct. We have two main types of polarization, E modes and B modes. E modes are easier to detect. They're correlated with the temperature anisotropies and arise from simple Thomson scattering in the plasma.
B modes, however, are the holy grail.
They are far weaker. They represent a twist or rotation in the light polarization. Standard density fluctuations don't produce B modes.
What does?
They're expected to be generated by two things. First, by gravitational lensing of the existing E modes, which has been detected. Second, and most excitingly, B modes are the predicted signature of primordial gravitational waves, the massive ripples in spacetime produced during cosmic inflation, moments after the Big Bang.
So detecting those would be direct evidence of the inflationary
A
theory.
huge discovery.
So the universe's background temperature is about 2.7 K, but we have found spots that are naturally colder than that background radiation. What is the record holder for the coldest natural place ever measured?
That title belongs to the Boomerang Nebula, about 5,000 light-years away. Observations show its temperature is approximately 1 Kelvin or minus 272 degrees Celsius.
That's significantly colder than the CMB. How does a single object get colder than the general background radiation of the entire universe?
The mechanism is a powerful, naturally occurring form of the same evaporative cooling used in our labs. The nebula is a pre-planetary nebula that's dying, and it is expelling gases at tremendous speed.
Something like 500,000 kilometers per hour.
An incredible speed. And this catastrophic rapid expansion over the last 1,500 years has caused the gas to cool adiabatically, dropping its temperature below the cosmic background. It's a massive natural refrigerator.
It's astonishing that the coldest place in the universe is colder because it's rapidly expanding, echoing the cooling principle that governs the universe itself.
And just for a final comparison, the coldest known large object in our own solar system is the dwarf planet 90377 Sedna, with an average surface temperature of 33 Kelvin.
Still much warmer.
Much warmer. But the absolute coldest pocket measured in the solar system is the Hermite crater, near the Moon's North Pole. Because regions within this crater are in permanent shadow, temperatures have been measured as low as minus 249 degrees Celsius. Still warmer than the cosmic background, but locally, the coldest spot we have confirmed in our neighborhood.
We've seen that the world record of 38 picokelvin was achieved by dropping an experiment down a tower. That confirmed that the biggest obstacle to sustained ultra-cold research on Earth is gravity.
Which brings us to the International Space Station. The ISS is the ultimate venue for cryogenics.
Microgravity eliminates all those gravity-related complications, convection currents, sedimentation, allowing physicists to study these delicate quantum systems for extended periods.
Right. And NASA recognized this need by launching the Cold Atom Laboratory, or CAL, to the ISS in 2018.
CAL is essentially a fully contained quantum physics lab in orbit, capable of producing Bose-Einstein condensates at temperatures between 40 and 70 billionths of a degree above absolute zero.
And that sustained microgravity environment is key. On Earth, we could hold a BEC for milliseconds. In orbit, the holding time increases to seconds and potentially much, much longer.
What specific ultra-cold research is this enabling that we just couldn't do on Earth?
The CAL team recently achieved a major milestone, creating and studying dual-species BECs using rubidium-87 and potassium-41.
Two different types of atoms in the same condensate.
Yes, and this is transformative for fundamental physics. By studying two distinct quantum test masses, they can study their respective interactions with gravity.
I assume this is a precision test of Einstein's general relativity.
That's the primary goal. They're testing the universality of freefall, or UFS.
The idea that all objects, regardless of their mass or composition, fall at the exact same rate in a gravitational field.
We verified this with classical masses to incredible precision, but CAL is testing it using quantum matter waves.
Does the theory of gravity hold true even when the matter's behaving like a single, gigantic quantum wave?
That's the question. Using these dual-species BECs, the scientists measure the tiny difference in the acceleration of the two atomic species as they fall in Earth's gravitational field. A violation of UFF could open the door to a quantum theory of gravity.
And beyond gravity, the ultra-cold environment is being applied to some of the biggest open questions in physics.
Absolutely. The goals are highly ambitious. For example, the unique stability offered by CAL allows researchers to explore quantum chemistry, how ultra-cold molecules interact in ways previously impossible.
And what about the big cosmological questions? Dark matter and dark energy.
The ultra-cold atoms in CAL can function as extraordinarily precise inertial sensors, atom interferometers in space, which are sensitive enough to detect minute gravitational signals.
So they're using these BECs to search for potential signatures of dark energy or dark matter.
That's the idea. If the constants of nature slightly fluctuate, or if dark matter particles interact minimally with regular matter, these changes could potentially be detected by the highly stable quantum matter waves produced on the ISS. The target is to push the CAL setup to 1 picokelvin in orbit.
The journey from using air pressure measurements in the 18th century to building a quantum lab in space designed to detect dark matter signatures is frankly breathtaking.
It confirms that the drive to conquer cold is truly a driver of fundamental understanding.
We have completed our deep dive, journeying from the philosophical quest for the primum frigidum with Robert Boyle through that intense 19th century rivalry that gave us liquid helium.
And now to the modern achievement of 38 picokelvin in a German drop tower.
We've established that the expansion of the universe naturally settled the entire cosmos into a frigid background of 2.725 Kelvin, the cosmic microwave background.
And that the only reason matter can be studied at temperatures below that is by using the precise techniques of laser cooling and the unique environment of microgravity.
The constant, frustrated drive to approach absolute zero forces us to confront the very nature of matter. It reveals that the laws of physics impose an inherent residual energy, the zero-point energy.
And that ultimately leads to matter exhibiting entirely coherent macroscopic quantum behavior like Bose-Einstein condensates. The boundaries of cold truly are the boundaries of our fundamental understanding.
So here's our final thought for you. We spent this entire deep dive establishing that absolute zero is fundamentally unattainable, that no system can be colder than 0K.
But the quantum world, in its infinite capacity for paradox, introduces the concept of negative thermodynamic temperatures.
And this flips the conventional understanding entirely.
It does. When physicists refer to a system having a negative temperature, and this is only possible in specialized isolated quantum systems, like collections of nuclear spins, they are absolutely not suggesting it is colder than absolute zero.
Wait, if it's not colder than zero, is it hotter?
Paradoxically, yes. A negative temperature system is hotter than any system with a positive temperature.
How can that be?
It arises because in these bizarre systems, the population of high-energy states exceeds the population of low-energy states. If you add energy, the system's entropy actually decreases, which is the reverse of normal physics. It forces the temperature scale to invert and go through infinity to become negative.
That is deeply counterintuitive. What is the physical proof that this negative temperature system is actually the hottest thing around?
The most direct evidence is the direction of heat flow. If you put that negative temperature system in contact with a positive temperature system, say one that is 100 Kelvin heat, will spontaneously flow from the negative system to the positive system.
Heat flows from negative to positive.
Thermodynamically, negative temperature is located at the top of the temperature scale, being hotter than infinity.
That is a fantastic, mind-bending conclusion. Even when we define the absolute bottom limit of cold, the rules of the quantum mechanical universe can turn the definition of hot and cold entirely upside down. It guarantees that the research will never truly end.